An ellipse is the set of all points, the sum of whose distances from two distinct fixed points called the foci is constant. Now, if we were drawing these, we've already talked about a locus or a collection of points. When we worked with the parabola, we were saying that it was the collection of all the points that were equidistant from the focus and the directrix, right? So we could do something similar with our ellipse. If I have a focus here and a focus here, let's say that I put like a thumbtack right here and a thumbtack right here, and I draped a string in between them. I wouldn't pull it tight, but I would just kind of leave it loose. If I took my pencil then and I pulled that string tight and put a point here, and then pulled it tight again here, it would put a point here, and pulled it tight again here, and here, and here, and here. That collection of points then would create the ellipse. And so that's what they're saying when they say it's the set of all points, the sum of whose distances from two distinct fixed points, the foci, is constant. The distance doesn't have to be the same. My string might be 5 inches long. The total distance of 5, the sum, is what has to be constant. But when I take the string and I stretch it right here, this piece of the string might only be 1 inch long and this piece of the string might be 4 inches long, but it still adds up to 5. Whereas when I stretch it right here, this piece might be 2.5 inches and this piece 2.5 inches, but the sum is still 5. That's what they're talking about. So we're not doing these constructions, but just to give us a little bit better understanding of what they're talking about in the definition. All right, two different types of ellipses. We have some ellipses that have their longer axis being horizontal, and some of them have their longer axis being vertical. So the major axis is just going to be defined as the larger axis. So if my larger axis is horizontal, then we say major axis horizontal, and it's going to have this equation and have a look like this. If my larger axis is vertical, then my major axis is vertical, and it's going to have this equation and have a look like this one. Now, really, the only thing that's different about these two equations is that A and B switch places, because A is always going to go with the major axis. So if A is with the x value, then it's major horizontal. If A is with the y value, then it's major vertical. All right, a couple of other things about these ellipses. A is going to be the distance from the center to the end of a major axis. So if I start here at the center and I go out to the end of that major axis, that distance between those 2 points is A. And the end of the major axis is called a vertex. If we have more than one of them, of course we'll have two, then they're called vertices. All right? B is the distance from the center to the end of the minor axis, the shorter axis. And C is the distance from the center to the focus. So from the center to that focus that we were just talking about a moment ago with the push pins. There's also an equation that relates A, B, and C. And because it's an equation, you can write it several different ways. Like I've got B squared equals A squared minus C squared in the textbook, but I could solve that if I wanted to for C. So if I go through and I solve that for C squared, I'm going to have C squared equals A squared minus B squared. Or I could solve it for A squared and move that B squared to the other side. You can turn it around any way that you want to. When we get to section 10.3 and we're working with hyperbolas, the relationship between A, B, and C is just the Pythagorean theorem. A squared plus B squared is equal to C squared. So that's why, even though they write it this way in the book, that's why I wrote it this way, because I think it's an easy reminder for us. A squared plus B squared equals C squared for hyperbolas. A squared minus B squared equals C squared for ellipses. That's the only thing that changes about them. All right, 2A is the length of the major axis. If the distance from the center to the end of the major axis is A, distance from the center to the end of the major axis is A, that's 1A plus 1A, so that total length would be 2A. 2B is the length of the minor axis. So if the distance from the center to the end of the minor axis is B, distance from the center to the end of the minor axis is B, then that total length would be 2B. Your foci are always going to be on your major axis. So you'll notice over here they were on the horizontal, whereas over here they were on the vertical. And your eccentricity can be found by doing your C value minus your A value. That will always give you a number between 0 and 1 for ellipses. Now, When we're talking about eccentricity just measures the elongation of an ellipse. You can have an ellipse that looks almost like a circle. It's so close to being a circle, it's just a tiny bit off of being perfect. That is going to have an eccentricity close to 0. So when it's close to 0, going to look like a circle. All right. Whereas if you take that circle and you pull it in both directions, you elongate it, then that's what's going to have an eccentricity of a larger value closer to 1. So that's what that number measures for us. Let's go down to example number 2, where they give me an equation and they ask me to give them several components. Example 2 says, sketch the ellipse given by the equation and identify the vertices. All right. So when I first look at this, that does not look anything like either of these two equations up here. Well, that's because for an ellipse, or a hyperbola for that matter, to be in standard form, they have to be set equal to 1. So the first thing that I'm going to need to do to get these set equal to 1 is I'm just going to divide both sides by 36. So if I go through and I divide both sides of my equation by 36, then it starts looking a little better. All right, I need to know which of these two scenarios I'm dealing with. So I got to figure out which is my major axis. We said that the major axis is going to be the larger axis. So when I look down here, I'm going to compare the two denominators. Because 36 is larger, that means that 36 is going with the major axis. And because 36 is paired with the y, then that means that the major axis is vertical. If 36 had been underneath x squared, then the major axis would have been horizontal. It's whatever it's paired with. All right, so if this is the equation that I'm working with then, major axis vertical, notice that what's under y squared is a squared. So down here, what's under y squared for us is 36. So if a squared is 36, what's a? 6, yes. And same thing, what's underneath x squared is b squared. So what's underneath x squared for us is 9 squared. So what's, it's 9 squared, yeah, 9. So what's b? 3. To find my center, the center of an ellipse is exactly like the center of a circle. Remember when we worked with circles and the center of the circle was HK? And H was the value subtracted from X and K was the value subtracted from Y. Exact same setup for ellipses. All right. So when I come down here, I have nothing being subtracted from X or Y. So in this case, my center is just going to be 0, 0. So let's go plot what we know. I know that I have a center at 0, 0. So I'm going to put that on my graph. I know my major axis is vertical and A is 6. Now, since A is the distance from the center to the end of the major axis, then I'm going to start at 0, 0, and I'm going to go vertically up 6 and vertically down 6. And those will be the endpoints of my major axis. Those will be my vertices. Since they asked me to give the values for the vertices, then I can look at this and go, okay, that's at 0, 6, and that's at 0, negative 6. So those are my vertices. B was the distance from the center to the end of the minor axis. So if B is 3, I'm going to start at my center and I'm going to go 3 horizontally since that's my minor axis. So 3 right and left. And then I've got the guide points that I need to sketch my ellipse. So for example 2, they had asked me to sketch the graph, give the center, give the vertices. We've done that. All right, look at example number 4. For example number 4, let me preface this by saying I cannot think of a more difficult example that we will see with ellipses. I tried to find one where they threw everything at us that we could possibly encounter with these. This is as bad as it gets. If we're okay with this, we got it. Okay? So to begin with, of course, they're not going to give me the equation in standard form. I'm going to have to, just as we did recently with the parabolas, I'm going to have to complete the square to get this in standard form. And with an ellipse, you'll notice that I have an x squared and a y squared. So exactly like we've done several times already this year with a circle, we have to complete the square twice. All right? So to complete the square twice, I'm going to get all of my x's together and leave room to complete the square. I'm going to get all of my y terms together and leave room to complete the square. And I'm going to get that constant out of the way and move it to the other side. So I'm going to add 8 to the other side. So I've got all my x's together, got all my y's together, moved the constant to the other side. When we complete the square, the leading coefficient has to be 1. And right now I have a leading coefficient of 4. I don't want to divide both sides. With parabolas, yeah, I can divide both sides. But I can't do that here because look what happens. If I divide this side by 4, that fixes the coefficient of x, but then it messes up the coefficient of y, right? Because the coefficient of y just became 1 over 4. So I don't want to divide by that 4. What I'll do instead is I'll factor it out. So I'm going to take out that 4. And so that means I have to take it out of every single term. So take the 4 out of 4x squared and take the 4 out of negative 8x. Now my leading coefficients are 1, so now I'm ready to complete the square. So let's start with this first one. To complete the square, we take the coefficient of the middle term, negative 2. We cut that in half, negative 1. We square it, positive 1. And we add that to both sides. Say that one more time. Take the coefficient of the middle term, negative 2. Cut that in half, negative 1. Square it, positive 1, and add that to both sides. But hang on. This 1 that we just added right here is inside parentheses that are being multiplied by 4. So when I inserted that 1, I inserted 1 inside parentheses being multiplied by 4. What did I really add to that side? 4. So I need to add 4 to the other side to balance that out, not 1. All right, let's complete the square for y. We're going to take the coefficient of the middle term, 4, cut it in half, 2, square it, 4, and add that to both sides. And this time, those parentheses out in front of them, I only have a 1. So all that I did was add 1 times 4. I genuinely did add 4. So I'm going to add 4 to the other side to balance it out. All right, so the purpose of completing the square is to create perfect squares, right? So what is this perfect square? X squared minus 2x plus 1. X minus 1 squared, right. What is this perfect square? Y plus 2 squared, exactly. So I'm going to have that 4 times x minus 1 squared plus y plus 2 squared, and then we had 8, 4, and 4 to give us the 16. Almost there. At this stage, we're back to the very first example that we saw today. Remember the first example, it was set equal to 36, and we said in standard form it has to be set equal to 1. So we divided everything by 36. Same idea here. I need this set equal to 1. So I'm going to divide both sides by 16 so that this is set equal to 1. And finally, I'm to my starting point, right? I've gone through all of that work just to get it to the point that I'm ready to begin. All right, so I need to figure out which of these two scenarios I'm working with, major axis horizontal or major axis vertical. So which one is it? Vertical. How did you know? Your 16 is bigger than your 4, right? And 16 is paired with y, so that means major axis is vertical. If the 16 had been under the x minus 1 squared, my major axis would have been horizontal. All right, now I need to know my center. And again, remember my center is HK. We treat it just like we did a circle. So what's my center going to be? 1, negative 2, right. So it's like the opposite of the negative 1 and the opposite of the positive 2. Positive 1, negative 2. If I pair this equation with the major axis vertical equation up here, I can see that a squared is under the y squared, and we have 16 under the y squared, so what's our a value going to be? 4. And we've got b squared under x squared, so if we come down here, we've got 4 under x squared, so what's our b value going to be? 2. And to find c, I could use the equation up here that equates a, b, and c. So I could say, okay, if b squared is equal to a squared minus c squared, I know b squared is 4 and a squared is 16, so I can solve for c squared. So c squared would be 12, take the square root of both sides, and we'll get plus or minus the square root of 12. Square root of 12 is square root of 4 times 3. Take out the square root of 4, and we've got 2 square roots of 3. Now, even though it says plus or minus, we're talking about c as a distance. Distance is always positive. So you'll notice for a, b, and c, we're always going to list them as the positive value. Yeah, for c, we're going to go up and down that value, or left and right that value. So you could think of it as plus or minus that way if you wanted to. All right, so let's plot what we know. We know that our center is 1, negative 2. So let's go ahead and graph that. 1, negative 2. There's our center. And we need our vertices. Since our major axis was vertical, I'm going to start right here at my vertex, and I'm going to go up my a value of 4, and I'm going to go down my a value of 4. Now, there are some of you that you're more visual, so it's actually easier for you to sit right here and go 1, 2, 3, 4, put a dot. 1, 2, 3, 4, put a dot. Okay, now where am I? There are others of you that you're more algebraic, and so it would be easier for you to say, okay, if I started at 1, negative 2, since I'm going up and down, I'm altering my y value. So what would negative 2 plus 4 be? What would negative 2 minus 4 be? So whichever one works for you is perfectly fine. If you're more visual, plot the points and then count and see where you are. If you're more algebraic, then look at your value and just add or subtract from that value. All right, then our b value is 2. So again, if we start at that center and we go 2 to the right and 2 to the left and plot those points, then we'll have the guides that we need for our sketch of our ellipse. Now, on the last example, they did not ask us to find our foci or our eccentricity, but they do here. So let's work on the foci. If I start at my center, they told me that C was the distance from the center to the focus, and that the foci are always on the major axis. So I'm going to start at the center, and if they have to be on the major axis, that means I'm going to go up and down, right? So I'm going to start at the center at 1, negative 2. And I'm going to go up 2 square roots of 3, and I'm going to go down 2 square roots of 3. So again, up, down, that alters the y value, right? So that means that I'm going to start at negative 2, and I'm going to go up 2 square roots of 3. That's plus 2 square roots of 3. And negative 2 down 2 square roots of 3 would be minus 2 square roots of 3. You can literally write it that way. You can write negative 2 plus 2 square roots of 3 and negative 2 minus 2 square roots of 3. If it's easier for you to get a decimal for that, that's perfectly fine as well. If you'd rather go through and figure out what 2 square roots of 3 is and then go through and add that to the negative 2 and subtract it from the negative 2 and plot the decimal versions, that's fine. Whatever's easier for you. Either one's fine with me. All right, and then the last thing that they wanted was our eccentricity. Our eccentricity is our C value divided by our A value. So our C value, remember, was 2 square roots of 3, and our A value was 4. So we can put 2 square roots of 3 over 4, reduce, and we've got square root of 3 over 2. So again, that's as bad as they get.